All right. Well, happy Monday. Good morning, and it's week 6. Time is just ticking right along. Yeah. Okay. So last week we wrapped up neural networks. We covered a bit of stuff on maximum likelihood estimation. Because that's another approach that you can take for machine learning. All of these things, we're optimizing different things, right? We're either trying to minimize, the cost function, or maximize the likelihood. We did that for what do you call it? Regression problems where the output is numeric, and so you would measure, cost as a distance, and you can kind of shrink that distance. We have a whole different set of problems, and these are classification problems. And in classification problems, our outputs are categorical, okay? And so in our examples, and I'm using the notation from our textbook, we have our observed data, our training data, okay? And, we have n observations in, some dimension d, okay? And each of these observations have a categorical label, okay? And we call these categorical labels T sub n, and our book labels them, category 1, category 2, ... to some letter C, okay? And our goal is that if we get a new observation, okay, that we'll be able to predict the category that it belongs to, okay? One thing to note is that these categories, we use integers, category 1, category 2, and whatnot, but they are not numeric. So category 5 is not more than category 4. And category 4 is not closer to category 5 than category 1 is, or anything like that. So don't treat them as numbers. It doesn't make sense to try to predict a value like 2.5 or something. This makes sense in regression numeric context, but not categorical ones. We are going to cover the Bayes classifier today, and the Bayes classifier uses Bayes' rule, the probability rule, for conditional probabilities, okay? It is what we call a probabilistic classifier, in that it is going to return a vector of probabilities. So if you have 3 possible labels, and I'll call these, category A, category B, and category C, what it will return might be something like a vector of the numbers 0.19, 0.8, and 0.01, so that the vector adds up to 1. Okay. Logistic regression is another example of a probabilistic classifier because it always returns a value between 0 and 1, and that can be interpreted as the probability that it belongs to a particular class. There are also other classifiers. So we have these non-probabilistic classifiers, and they use these quote-unquote hard rules without any kind of probability, and it'll just say something like, our model predicts observation 1 is class B. No probability assigned there. And we'll take a look at some of those later. We have k-nearest neighbors, which is a very common classifier, as well as support vector machines, okay? And then one thing to note is that this is called the Bayes classifier, and it extensively uses Bayes' rule, but it is not considered Bayesian statistics. So that's like an entirely other subfield of statistics. And I cover Bayesian statistics in 102C. Monte Carlo methods I would say Bayesian stats is, one of the number 1 applications of Monte Carlo methods. Okay, so this should be review from, what is this, Stats 100A, your probability rules. And so you have Bayes' theorem, and we have the conditional probability, and we say the probability of A given B can be calculated by taking the numerator, which is the probability of the intersection of A and B, okay? And that value, the probability of the intersection of A and B, can be found by doing the probability of B given A times the probability of A, and then we'll divide by the probability of B, okay? And if you have, kind of different kind of possible outcomes for A, right? And we have, we can decompose it into, A sub 1, A sub 2, A sub 3, or, A sub whatever. This bottom part for the probability of B can be found by, kind of the law of total probability. This part is basically equal to the probability of B intersection A sub n, and then you take it across all of the different possible values of A, and that will basically give you the total probability of B, okay? So the denominator, if you think about that, the denominator is equal to the numerator summed across all of the different possible values of A, okay? So we have that, okay? And so we will apply Bayes' rule to a classifier problem. And so this is going to be the probability that we want to calculate. We want to calculate the probability that a new observation belongs to class C, okay? So, what is the probability that this new object that I'm seeing belongs to, category A? And that is going to be based on or given the features or the kind of the values in our input vector, which we'll call x new, okay? As well as given all of the training data that we have so far. So this is what we want to find. So we want to find the probability that an observation belongs to class C given its input values in x new, and as well as all of the training data in x and t. The output, okay, this thing that we want, it's a probability, so all of the rules of probabilities apply. So it's always going to be a value between 0 and 1. So that's just kind of your base sanity check. If you're getting a number that's outside of the range of 0 and 1, you've likely done something wrong, okay? And the probabilities all have to add up to 1. So if you think about all of the different possible classes that you have, the sum of those probabilities must add up to 1. So again, if we have 3 classes, class A, B, and C, you're going to get 3 probabilities, and they have to add up to 1. So an example is A is 19%, B is 80%, and C is 1%, so that they add up to 1, okay? All right, so, Bayes' rule is the probability of A given B is equal to the probability of B given A times the probability of A divided by the probability of B. So the A part is going to be what is the probability that the new observation belongs to a certain class, okay? And then the B part is going to be the values that we have in x new, okay? So it's going to be, we're going to rewrite this. So this is, we call this part over here, this is known as the posterior, okay? It is the probability that we want to find. And we're going to swap the A and the B, okay, to get this part, the probability of B given A. And this we call the likelihood. And it's the probability of x new given that our label is class C, okay? So we're going to say, so we want to know, what is, if somebody is, I don't know, let's say we're trying to classify whether, the breed of a dog based on its size, okay? Like its height and weight, all right? And let's say your 3 possible breeds are Chihuahua, I don't know what's a medium-sized dog, Border Collie, and a big dog, German Shepherd, or something like that, okay? So let's say those are the 3 things, and I don't know, well, how big is a German Shepherd? Like 70 pounds? I don't know, okay? And a Border Collie is what, 40 pounds? I don't know. And then a Chihuahua is like 10? I'm just making up numbers here, okay? So let's say we get, so the goal is, what is the probability that if I observe a dog that's 45 pounds, okay, right? So our X new coming in is going to be like 45, and we want to know, okay, what's the probability that it's a Chihuahua? What's the probability it's a Border Collie? What's the probability that it is a German Shepherd, okay? And so just kind of based on that, we'll go, okay, most likely it's going to be a Border Collie, okay? And then, but the way we're going to calculate that is we're going to get the likelihood, which is if it were a Chihuahua, what's the probability you get a 45-pound dog? If it were a Border Collie, what's the probability you get a 45-pound dog? If it were a German Shepherd, what's the probability you get a 45-pound dog? So you're kind of switching from, if I have this number, what's the probability of the label or the category, versus swapping it around, if we had a dog of this category or breed, what's the probability I get this X value? Okay, so that's the likelihood. It's the probability of observing the observed value if we assumed the new observation belonged to a specific class. Then we also multiply it by our prior probability. Okay, it's the probability that some new observation belongs to class C before you know anything else about it. So you might, like prior to your data, you might know that some class is more likely than others or something like that, and that's going to be your prior. And then this down here, this is our marginal probability, and it's the probability of getting of observing our values X regardless of the class label. And the purpose of this is just so that everything adds up to 1. Okay, so yeah, I guess this is what I'm saying on this side. So we'll apply the law of total probability and can take advantage of the fact that the probabilities across all possible classes must sum to 1. And so what we're going to do is we're going to take our numerator and we're going to just say our denominator is going to be equal to the numerator summed across all possible classes. And so, the formula for it looks kind of messy, but it's basically we're going to try out C prime, okay, basically for all of the different classes. So we're going to say, all right, what is the probability of, this thing if it were a Chihuahua, plus what's the probability of, this value if it were a Border Collie, what's the probability of this number if it were a German Shepherd or something like that, okay? All right, so just to kind of illustrate this out, we'll go through a kind of a simple example of the Bayes classifier. And before we do that, let me give you your first view quiz answer, which is the letter D. D as in dog. Let me just double check this. Yeah. Okay. So this is silly, but let's say you decide to purchase, I don't know, pouches of marbles, right? So you go online and you say, I'm going to order marbles. And they say, you're going to get a mix of red and blue marbles. You order 25 pouches of marbles from some arbitrary company. And then when they arrive, I don't know, the pouches say like made in, this particular factory, right? You get some kind of serial number or something, and it's like, and it says, okay, this one came from factory A or factory B or factory C. So we see that the pouches are filled at 3 different factories, and each of these factories maybe has a different filling proportion of red and blue marbles, okay? And so in our shipment, we have 24 pouches, and they're labeled with their factories. Half of them, 12, came from factory A, and then a quarter came from factory B and C each. So 6 came from factory B and 6 came from factory C. And then our last one, bag number 25, is not labeled, and we're going to try to guess which factory it came from. And we are going to assume that the bags are filled basically by kind of a Bernoulli or binomial process, and that, like, there's, I don't know, some population of marbles, a mixture of red and blue marbles at the factory, and they just kind of independently select them to fill your pouch, okay? So this is 25 bags here. 24 of them are going to serve as our training data, and this is going to be our one test case over here. And so you go through the process of basically counting up all of the data in your training data, okay? So you dump out the marbles and you count them, and when you look at all of the marbles that came from factory A, okay, you get that 60% of the marbles are red and 40% are blue, okay? And then when you do it for factory B, 50% are red and 50% are blue. And then when you do it for factory C, 40% are red and 60% are blue. So based on this, you know, we're gonna kind of assume with like if this is our observed data, our maximum likelihood estimates for each factory is basically going to be, you know, 60% for factory A, 50% for factory B, 40% for factory C. Okay, so we don't work at the factories. We don't know exactly what proportion at factory A are red and stuff. And you know, when we open up the pouches, they're not all exactly 60% red, right? So some might have a little bit more red, some might have a little less red, but on average, we get 60% red, okay? And then we'll say they don't cause any concern about the marble selection being a result of the binomial process. So I said, for example, one pouch might have 70% red, 14 out of 20, and another pouch might have 11 out of 20, 55% red, but when you average everything together, you get 60% red, okay? And so we'll just assume, based on the data we've observed, that factory A fills its pouches with something around 60% red on average, okay? But subject to randomness and, you know, kind of a random binomial process. So our summary stats are also going to be our maximum likelihood estimates for the filling proportions based on the training data that we have, okay? So we go to our test case and we open up the pouch, and when we open up this pouch, there's 20 marbles and 10 of them are red, okay? And so based on this, which factory do you think it came from, okay? So here we're going to calculate the likelihood. The likelihood is, what is the probability of getting our observed data, in this case 10 red marbles out of 20 marbles total, if we assumed it came from factory A, or if it came from factory B, or if it came from factory C, okay? And so this, we just calculate our likelihood using the binomial probability, and we're going to change the value of P based on which factory, okay? So we're going to say, what is the probability of getting 10 red marbles out of 20 marbles? So that's going to be 20 choose 10. And if it came from factory A, it's 0.6 to the 10 times 0.4 to the 10, and you get 0.117, okay? If you have factory B, you're going to have P is 0.5, so 50% red, 50% blue, okay? 0.5 to the 10, 0.5 to the 10, and that's 0.176. And factory C is going to be 20 choose 10, 0.4 to the 10, so factory C is 40% red. So what's the probability? 0.4 to the 10 times 0.6 to the 10, and we get 0.117, okay? So based on the likelihoods only, the factory with the highest likelihood is factory B, which makes sense, right? Because factory B in our training data produced bags that were 50% red. And so when our test case is 50% red, it looks most similar to factory B, okay? But we also say, well, you know, factory A is 60% red, factory C is 40% red. So it is also possible, okay? There's still a high likelihood that it came from either factory A or factory C, because of randomness, even if factory A is 60% red, it's very possible to make a bag that's only 50% red, okay? And vice versa for factory C, okay? But we want to balance this likelihood, which says factory B has the highest likelihood, with our prior knowledge, our prior probabilities, which was before we opened up any of the bags, if I didn't tell you anything about the contents of the bag and I said, hey, what do you think it came, what's the probability that this bag came from factory A or B or C? Okay. Well, we might base that based on our training data. And in our training data, out of the 24 bags, 12 of them came from factory A. So before I actually looked at the contents of the bag, I might have said the chance that a brand new bag that I have no idea anything about, we're going to say is 50% factory A. Okay, and then, you know, factory B and factory C, they each had 6 bags out of the 24. So we might say, you know, I'm going to guess that it's 25% factory B or 25% factory C. Okay, so we want to kind of balance kind of these two parts, the prior and the likelihood. Okay, so the likelihood says factory B is the most likely based on opening up the bag and seeing that it's 50% red, okay? And then the prior probability said, well, before you even opened up the bag, you just know that factory A, you know, produces about half of the bags, okay? So we balance these two things just by multiplying them together, okay? So we calculate the numerator, which is going to be the likelihood, okay? This is found using the binomial probability, times the prior, and this is just using basically the proportions of the labels. Okay, so I'm going to take my likelihood for getting 10 marbles from a factory that has 10 red marbles from a factory that has a 60% filling rate of red, multiplied by the prior probability of 0.5, and I get 0.0585. And then for class B, the likelihood was 0.176. This is the probability of getting 10 red marbles, or 50% red marbles if it comes from a factory that fills with 50% red marbles. But we're going to multiply that by the prior probability of 0.25. And then we do the same thing for factory C, and we get 0.117 times the prior probability of 0.25. Okay? And so these are the resulting numbers, 0.0585, 0.044, and 0.0292. And that's almost our answer, okay? These are the relative, I guess, I don't know, probabilities or densities or something. But what we need is we need everything to add up to 1, okay? We need all 3 of these numbers. We got to scale them up so that their relative proportion is, or relative size is the same, but that they all add up to 1. So the way we're going to do that, like if you didn't even see the formula, what you would do is you would add these up, get that total, and then you would divide everything by that total, and then you would know everything adds up to 1. Okay, and that's exactly what we do in with Bayes' rule. Okay, so with Bayes' rule, we say the marginal probability. This is what's the probability of getting our observed values. That is 10 red marbles out of 20. In a bag of 20 marbles, okay, regardless of class label. And so we apply the law of total probability, and we're going to find the marginal probability by basically summing the numerator across all possible classes. So this number, 0.0585, is the numerator for class A, and then we'll add 0.044 for the numerator for class B, and 0.029, the numerator for class C. And so our denominator is going to be 0.1319. And then, so we do it for class A, and if I take 0.0585 divided by this, 0.131, we get basically 0.444, okay? So this is, so in short, again, our Bayes' rule says, what's the probability that our new observation belongs to class A, given the observed data, 10 red out of 20, okay, and all of our other training data. And that's going to be found by finding the likelihood. What's the probability of getting 10 red if it came from class A, which has a filling proportion of 60%, times the prior probability of coming from factory A, so that's 0.5, and this is the binomial probability. And then getting 10 red regardless of factory, that's going to be the sum of the numerator across all possible classes, So we get that, and we get 0.44. You do this for the other two classes, Class B and Class C, and you get 0.334 and 0.222. And so this is our posterior distribution. This is our Bayes classifier. So our Bayes classifier says 44% chance it's red, 33% chance it's B, 44% chance it's Class A, or Factory A, 33% chance it's Factory B, 22% chance it's Factory C. Okay? So just to kind of take a step back, and our test case that we observed is 20 marbles, 10 of them are red, so it's 50% red. Okay? And so if we were to base our classification based only on that information, we would probably pick Factory B, because in Factory B, in our training data, Factory B produced 50% red. So our observation most closely matches Factory B. Okay? But with the Bayes classifier, we want to take into account the prior probabilities prior to looking at our data. And in our training data, we saw that half of the bags came from Factory A, whereas only a quarter of the bags came from Factory B. Okay, and so when you and then the likelihood calculations show that getting 50% red from a factory that has a 60% filling proportion is not all that weird, and so it balances out. Okay, so basically this number where we say, hey, what's the probability that it came from Factory B is 0.334. That's basically kind of a compromise between the two parts. So prior to looking at the data, our guess that it came from Factory B was 0.25. Okay? After looking at the data and seeing our bag most closely resembles Factory B in that it's 50% red, we kind of adjust our number from 0.25 to something a little higher, to 0.334. Okay? Similarly, this number over here for Factory A of being 0.444 reflects kind of the compromise as well. Prior to looking at the data, what's the probability a bag came from Factory A? We said 50%. Okay. After we open up the bag and we see, oh, you know what, the contents of this bag looks more closely to Factory B, we adjust it down from 50% down to 0.44, 44%. Okay. There are a few, I guess, strong assumptions. And anytime somebody says strong assumption, this is actually a bad thing, okay? Meaning, like, you have to kind of be very confident about justifying these assumptions, okay? So one is, so two of the big assumptions. One of the assumptions was that the training data I have is like representative of the factories, right? We said, because when I opened up all of the bags that came from Factory A, and the marbles were 60% red, I'm assuming Factory A has a 60% red filling rate. And then I looked at my training data, and for Factory B, half of them were red, and so I'm assuming Factory B has 50% red. That's, I don't know if that's a great assumption. And you can kind of relax that assumption a little bit if you want, with like a fully Bayesian approach, but that's beyond the scope of our course. The other big assumption was that because I ordered 24 or 25 bags, and 24 of them were labeled, and 12 out of the 24 came from Factory A, I'm assuming Factory A, is responsible for 50% of marble production out there, or something like that. Okay. And so that assumes our sample is representative of the class proportions. And again, that could be wrong, okay? So, I wrote, someone else might make entirely different assumptions. So, for example, if you have somebody with insider knowledge, they might know all three factories, Factory A, B, and C, all have the same output, okay? And that it's not like one factory is more productive than the other factories. So in that case, it's just kind of a weird coincidence that in our sample, half of our bags came from factory A and only a quarter came from factory B and a quarter came from factory C, because in, I don't know, worldwide production, really, factory B makes a third of the bags and factory C makes a third of the bags. So if you have knowledge like that, you would incorporate that instead, okay? But this is just a simple example, and so based on the data that we had, we're just assuming that, okay? I want to do just another example, almost exactly the same, except this time, my test case, I open up the bag, and there's 20 marbles, and only 6 of them are red, okay? So in my observed case, only 30% of the marbles are red. And so now we're going to calculate our likelihoods, and we're going to say, okay, what is the likelihood it came... What is the likelihood that it came from factory A? So we're going to say, what's the probability of getting 6 red if it has a filling proportion of 60% red? Okay, and so that we would do 20 choose 6, 0.6 to the 6, and 0.4 to the 14. Okay, so this is the likelihood. And then the prior probability for factory A is 0.5. Okay. For factory B, it's going to be 20 choose 6, 0.5. Factory B is 50% red. 50% red, we have 6 red. 50% blue, we have 14 blue. Okay, and then its prior probability is 0.25. So I'm just kind of skipping ahead, combining the prior and the likelihood. This is the numerators. Okay, and then for factory C has a fill proportion of 40% red. So we do 20 choose 6, 0.4 to the 6. It's going to be 60% blue, 0.6 to the 14, times 0.25 for our prior probability, and we get 0.03. And so our numerators are these values, and our denominator is the sum of the numerators across all possible classes, and we get, a small number, 0.042. Okay, so this is just saying the likelihood of getting our observed data, the marginal probability of just getting 6 red out of 20 marbles, is pretty small, only around a 4% probability across all possible classes. But we're going to take our numerators and divide it by our denominator to kind of scale all of these values up so that they add up to 1. Because right now they don't add up to 1, they add up to 0.042. So if you do this, the resulting posterior probabilities is it's going to be around 5.6% class A, 21%, 22% class B, and around 73% class C. Okay? And so in this case, class C is by far the most likely because according to our training data, class C has a fill proportion of 40% red. And so when your test case is only 30% red, it's much more likely that it's coming from factory C than factory A. Factory A it fills at 60% red, and so it feels very kind of unlikely. It's very improbable. We don't want to say impossible, but it's improbable that a factory that fills 60% red is going to produce a bag that's only 30% red. And so when our test case comes along and it's only 30% red, okay, even though factory A is responsible for half of the bags out there, okay, we're going to say, yeah, you know what, it's probably not coming from factory A. This sure looks a lot more like factory C, which has a fill proportion of 40% red. So even though our prior probability is only that a quarter of the bags come from factory C, our observations where our test case was basically only 30% red makes factory C the most probable class assignments. Okay. All right, let me give you your second view quiz answer, which is the letter B. B as in bear. B. Okay. So that is that's the Bayes classifier for, I guess, a simple kind of Bernoulli there's just one parameter of the fill proportion, and that's how we do that. Pay attention to this example. I'll talk about the midterm exam on Wednesday, but I know sometimes I go, oh, I can't believe I scheduled the second midterm and it's next week, right? So next Monday we'll have a midterm exam, and you can expect a problem similar to this. Okay, so this is these are some good slides to pay attention to. Okay, and we can use the Bayes classifier in many other contexts, and so I want to do a mixture of multivariate Gaussians, as we might often see numeric values, okay? And so again, our multivariate normal distribution has this PDF, okay? And we talked a little bit about this on Friday, and you know, your sigma matrix is your kind of your variance covariance matrix, and your off-diagonal elements are the covariance, the diagonal elements are the variance. If the off-diagonal element is 0, then those x variables are independent. Okay. There is a library that calculates, you know, multivariate normal densities and stuff very easily for us, and that is library MVT norm for multivariate normal, and it can also generate random multivariate values. And so I am going to generate values from 3 cases. We're going to have three, I guess, categories or classes. So we have class A, class B, and class C. The mean vector for class A is 2, 3. So, you know, just imagine your coordinate plane. So 2, 3, kind of in the upper right corner. For class B, the mean is 0, 0, so at the origin. And then for class C is going to be 2, -2, so it's going to be the lower right corner, kind of there. I don't know about corner, but so we have this is in the upper right at the origin, and this will be at the lower right. Okay, we have a sigma matrix for class A, and so the matrix, it's, you know, it's a 2 by 2, and this the way you write your matrix is the first element is top left, right? So the variance for x1 is going to be 3, and then the covariance is 0, and the variance for x2 is 1. Okay, so 3, 0, 0, 1. So that means x1 and x2 are independent because we have 0 here. The variance matrix for class B is the identity matrix, 1, 0, 0, 1. And so we have variance 1 for x1 and variance 1 for x2. And then here for class C, we have 3, 2.5, 2.53. So we have a lot of covariance between x1 and x2, okay? And we have variance 3 for x1 and variance 3 for x2. So I'm going to generate 30 observations for each of our classes, okay? And so my observed x values from class A are going to be these 30. I've got my observed xb and my observed xc, and I'm going to bind them all into one big matrix X, and this is just to kind of plot this. All right, so I'm going to plot all of these things. I'm going to color them. Class A will be red, Class B will be blue, and Class C will be green. And then these are, you're going to see ellipses to kind of draw out different percentile lines for the they're kind of like contour plots for the multivariate normal. And so I'm going to draw ellipses at kind of the 40th percentile, 65th, 80th, 90th, and 95th percentile. Okay? And so this is kind of my plot of the multivariate normals. And so the lines, this one is centered at 2, 3, okay, with variance in the x1 direction of 3 and variance in the x2 direction of 1. This one, these circles are centered at 0, 0, with variance in the x1 direction of 1 and variance in the x2 direction of 1. And then this one is centered at 2, -2, with variance in the x1 direction of 3, variance in the x2 direction of 3, but then we also see covariance between x1 and x2 of 2.5. Okay, so this one, so these ones are independent, and so they're, I guess the, I don't know, I guess the axes of the ellipse are perpendicular, whereas, or I guess, no, the axes of the ellipse are parallel to the x1 and x2 axis, and this one, the axes of the ellipse are perpendicular, but the axes of the ellipse are not parallel to x1 and x2, okay, indicating that there's covariance. And then, so the ellipses are the true values that we use to simulate the data, and then the dots themselves are our observed values. So we have random dots here, and based on the way the ellipses are drawn, we would anticipate approximately 40% of dots to be within the first line, approximately 65% within the second line, approximately 80, 90, and 95% of values to be within, 95% of our dots should be within our, last ellipse here, indicating, yeah, out of 30, we would expect 1 or 2 to fall out, okay? So this is our simulated data. And so what we want to do is we're going to have to estimate, based on our training data, we would have to estimate what is the mean and what is the covariance of each of these things, okay? So remember, our training data, we don't actually get to see these ellipses here that were used to generate the data. We only get to see the dots, okay? The dots are labeled, they are colored, red, blue, green, or by class A, B, and C, but we don't actually know, like, what is the mean of the distribution that generated these blue dots. So we're gonna have to estimate those. So we're gonna estimate them using just maximum likelihood estimation. And so maximum likelihood estimation for the mean is just the literal mean of, the values that belong to that particular class. So we're going to just say, okay, all of the observations that belong to class A, we'll take those, add them up, divide by how many we have, and we'll get our vector of means. So if you take class A, if you take these red dots here, the mean turns out to be 2.26, 2.82. The mean for class B is going to be 0.3 and negative 0.1. And the mean for class C is going to be 2.25 and negative 1.9. Okay, so the generating distribution was centered at 2, 3. So we're getting something kind of close, but not exactly that. Again, just because of kind of randomness. All right, and then as far as the maximum likelihood estimate of our variance matrix, okay, it's going to be basically you do x minus mu times x minus mu divided by 1 over n. You can do it in a kind of vectorized, and this will take care of the summation. So if you take the entire matrix and you do x minus mu transpose times x minus mu, and you do this will work, okay? But this is going to be biased, and so if we want an unbiased thing, we divide by n minus 1, and this is equivalent to using the variance function in R. Okay, so if you use the variance function in R, this is how it calculates it. Okay, it's going to do the unbiased estimate. And so here, I'm going to just take all of the observations that belong to class A, and I'm going to ask for its variance. And so I get a 2 by 2 matrix for A, B, and C. And so for A, the generating matrix was 3, 0, 0, 1, and we have 2.98, and then negative 0.18, negative 0.18, and 1.19. Okay, and then here for class B, it was the identity matrix 1, 0, 0, 1, and we have something kind of close to that, but not exactly. And then for class C, the generating matrix was 3, 2.5, 2.53, and these numbers are a lot smaller, but that's just because of randomness, okay? So here I'm going to plot our estimated contour lines, okay? So what you'll see here is that these ellipses look more centered to the actual data, right? So if you look at the blue dots, these kind of ellipses and circles, they look a lot centered, like they are centered around our blue dots. These are estimated based off of the data that we observed, okay? Same thing here, and same thing for the red dots. And here I can kind of overlay and compare them to our kind of known. So the known ones are the black ellipses in black, and then the estimated ones are the ellipses in orange. And they're similar, but not exactly. And again, because the orange ones are based off of our data, whereas the ones drawn in black are the ones that we picked out to generate our data, okay? All right, and so we're gonna run out of time, but what we wanna do next is, here I have a test case. Let's say we observe something where x1 is 0 and x2 is 0. Okay, so I draw this, this point right here. And I say, okay, based on our training data, do you think this is class A in red, class B in blue, or class C in green? And we look at this and we say, you know what, this, I'm quite confident it's going to be class B in blue, okay? But how, you know, we're visualizing this, and that's fine, but, you know, can we use our Bayes classifier to kind of give us that answer? And the answer is yes. We're going to use the Bayes classifier to calculate what is the probability that this observation belongs to class B if its x1 value is 0 and its x2 value is 0. Okay, and then we'll also calculate what's the probability that it comes from class A in red, and what's the probability that it comes from class C in green. Okay, because it's not 0 probability, right? It is possible. Okay, although unlikely, it's much more likely that it came from the class B in blue, but it is also possible that this dot out here, you know, was generated by, you know, class A in red. Okay, so we don't want to say it's 0 probability, but probably a low probability, right? And then, you know, we could try out different locations. You know, if you see like this dot right here is, you know, this, you know, red observed a dot there, or red produced a dot right there, but green also produces a dot here. You know, here's a dot out here, and this is actually produced by green, but it seems like it's more in red territory and stuff. And so we want to kind of calculate those probabilities, and we'll use the Bayes classifier. So that's so we will continue this on, I guess, on Wednesday, where we'll just basically apply our same formula, but now, you know, the likelihood uses a multivariate normal distribution. Okay, let me give you your third view quiz answer, which is the letter A as in apple, and we'll end there. And we'll see you guys on Wednesday. We'll go over topics for the midterm exam, and that will be that. Okay, see you then.